Okay, so today what we are going to talk about is net change, average change, and total change, and a little bit of position also. So still talking about integrals and accumulation. Let's start out first with net change. So we've already talked about net change before. This is a little bit of a review, but remember, net change is the integral from a to b of v of t dt, and that is going to tell us the net change in, we'll say, position or, oops, I spelled that wrong, position or amount, okay, from A to B. So otherwise known as our displacement. So we've already done this. I just want to review it so we can kind of compare it to what we're going to do now. So another way that we haven't really talked about, but another way to write net change is really going to be the distance between the initial or the ending position and the initial position. So if I have velocity and I find the position function and I just subtract the ending position from the starting position, that will give me the displacement, okay? So the integral from a to b of v of t dt does not tell us the total change. Okay. We think of total change kind of like the odometer on your car. So no matter whether you're going forwards or backwards, it's still adding change onto it. Whereas net change takes into account that positive and that negative. So just remember, that's going to tell us how far we've gone from the start. That's going to be your net change. Now, position. To find a particle or an object's position or amount at a specific point in time using integrals, let's say I want to find the position at B, and I'm given the starting point at A. So I know that the integral from A to B of v of t dt, that is going to give me the change, the net change in position from A to B. So if I know how much it's changed, all I need to do is add wherever it started. So I'm going to use x of t or whatever for x of a for position. You could see it as s of a, x of a, f of a, all that kind of stuff. So this is going to be the location or the position at A. So if I know where it is at A and I add how much it's changed, that's going to give me this location of it at B. Okay, which kind of actually goes back to what we talked about up here, where I said that the integral was x of b minus x of a. Well, I can easily subtract over that x of a and get the exact same statement. Okay, so anytime you want position, you have to take the initial position and add how far it's traveled from wherever you're looking to wherever you're ending. Okay, so we're going to practice a couple of those, and then we're going to go into average rate of change and total change. So a particle moves along the y-axis using this velocity function. Okay, I want to find the position at 2, but they're giving me that y of 0 is 3. So that means that at 0, the position is 3. We want to know, find the position at 2. So I want to take, okay, well, my starting point, if I'm going from 0 to 2, right, I know that I'm going to be doing the integral from 0 to 2 of v of t dt. Okay, that's going to tell me how much it's changed. And then I want to add to that whatever my initial position was. My initial position was 3. Okay? Now, what we can do from there is we can completely do that in the calculator. So let's put that into the calculator. Give me 1 second, I gotta get mine. So I'm going to do 3 plus, now I have to do math 9, the integral from 0 to 2. Now I'm going to do x, sine of x squared dx. And that is going to give me 3.0697, which, rounding to 3 decimal places, I'm going to say 3.070. So that will give me my final position. I'm completely using the calculator right now. We will learn how to do some of these by hand later on, but for right now, we're doing all calculator use. All right. Particle moves along a straight line. The velocity is given by this function right here, this funky thing. And we also know that s of 0 is 10. So write an expression involving an integral that gives the position, and use this to find the position at 5. Okay? So I know I'm starting at 0, and I'm ending at 5. Okay, so let's do the integral from 0 to 5 of v of t dt. Okay, and I know that at 0, I'm actually starting at 10. So this is my location to begin with, and this is how far I've gone. Okay, this is the start, and that's how far I've gone. So when I go and I put that into my calculator, and I want everybody to practice doing this, because you want to make sure that you guys have these calculator skills down. So try it. 2 to the 6/5 minus x to the 3rd. Okay, and you should come out, pause it, see if you can get this on your own. You should come out with negative 9.207. So remember, if your position is negative, are they giving us units here? I don't think they gave us units. Did they give us units up here? They didn't give us units either. So just remember that if it's negative 9, that's going to mean that it's to the left of the origin. That's what the negative is going to tell us. Okay? Any questions? Let me know. So from 0 to 12, a particle moves along the x-axis. The velocity is given by this function. Okay, the position at -2, the particle is at position -2 at time 0. So we're starting at 0, and we're ending at 4. Okay, and I know that the position is -2, but the x value that we're starting at is 0. So we want the integral from 0 to 4 of cosine of pi over 6t dt. Now, we know that's how far it's going to travel between 0 and 4, but if I want the position, I have to make sure that I take into account where it started. Now, I always put it in the front of the integral just because that's how I've seen it most of the time. If you put it after the integral, that's fine, but just make sure you do not forget your dt. So, in the calculator, and don't be afraid, guys, if you forget how to do this in the calculator, please make sure you're asking. You should come out with 1.999, okay, which I'm going to assume maybe if we were to do this by hand, we might come out with something closer to 2 as our answer. But 1.999, that's going to tell us that the position is to the right of the origin, because it's position, right? Okay? So that is how we are going to determine position. Net change position, we've done a little bit of. We're going to go into now the average rate of change and then the total change. Okay, so moving on to average rate of change. So the integral 1 over b minus a times the integral from b to a of v of t, or this is the same thing, we just multiplied this integral up to the top. Okay, so you might see it either of these two ways, is going to tell us the average value or the average So let me show you why. We talked about a second ago that this integral right here is actually going to be the position at B minus the position at A. That's going to give us the total change in the position, right? That's going to give us the net change. Now, if I take that, so this is a position function, but then I'm going to divide it again by the difference in the x values. I'm going to divide it by B minus A. Okay, that's basically going to be a position, and we're dividing by time again. So this is like our slope formula, right? Slope formula, this is going to give us the rate of change, or average rate of change, I guess we should call it. This is going to give us the average rate of change. Okay? Or the average velocity, or the average, whatever's inside of this integral is what it is going to give you the average of. So let me give you a few examples. If I gave you the 1 over b minus a, the integral from a to b of, let's say, x of t, or if I gave you 1 over b minus a, the integral from a to b of v of t, or if I even gave you 1 over b minus a, the integral from a to b of a of t. Okay, all of these three things are going to give us an average value. Now we have to realize this is a position integral, so this is going to give us the average position, or the average value. On the interval a to b. This is going to give us the average velocity on AB, and this is going to give me the average acceleration. On the integral AB. Okay, so notice here, A of t, it's average acceleration. X of t, it's average position. V of t, it's average velocity. And notice that all of these have this fraction in the front. So anytime you see a fraction in the front of your integral, or even below your integral, most of the time that's going to be showing average rate of change. So let's do a couple practice questions. The equation v of t equals 2t minus 3 models the rate in feet per second. Ooh, we got some units there. How fast a particle is moving. Find the average value. So we want to find this average value and explain its meaning. So I'm going to use the calculator to find that average value. 1/5 math 9 0 to 5 of 2x minus 3 dx. So 1/5 the integral from 0 to 5 of v of t dt is going to equal 2. Okay, so remember, I have a fraction and I have v of t, so that's going to be telling me the average velocity of the particle from 0 to 5 seconds. Okay, you always have to have units. The average velocity. Now make sure that our answer has units for velocity. So the average velocity of the particle from 0 to 5 seconds is 2 feet per second. Okay, units have to make sure that they're matching up. All right. Same thing here, okay? Feet per second, we're doing the average rate of change here. So I'm going to do 1 over, Now make sure here when you put this in the calculator, this 2 pi has to go in parentheses or else it's not going to calculate it right. So 1 over 2 pi, math 9, from 0 to 2 pi of the sine of x dx. So that's going to give me 0. Ooh, that's interesting. Let's think about this graph. If I have a sine curve, basic sine curve, from 0 to 2 pi, right? Remember, a sine curve is going to look like this, right? So if I want the average velocity, well, it's kind of moving forward and backwards the same amount. So like the speed up here, this is going to kind of cancel out with this area, right? Which I know that the total distance traveled is going to be 0. So therefore, wouldn't that mean that your average rate of change is also 0, right? So the average velocity remember, averages always align to directly what's inside that integral. The average velocity of the wave from 0 to 2 pi seconds is 0 feet per second. Okay, mainly the reason why it's 0 feet per second is because that net change, this right here, the net change in position is 0. So therefore, your average velocity is also going to be 0. All right, from 0 to 6, a particle is moving along the x-axis. The particle's position is not explicitly given, but the velocity formula is given to us, and the acceleration formula. We want to find the average velocity from 0 to 6. So, integral from 0 to 6 of v of t dt, that's going to give me how much it's changed. If I put a 1/6 in the front, that's going to give me the average. Now remember, it's always 1 over that difference. So let's say I was doing the integral from 1 to 6, it would be 1/5, okay? But 0 to 6 is a width of 6. And that, again, we can take right to our calculator. From 0 to 6 of 2 sine of e to the x over 4, close those parentheses, plus 1 dx. And you're going to come out with 1.081. They don't give us units here, so we're going to just give it that. Now, that's going to be telling us that the average velocity is basically positive, so that means that on average, it's going to be moving forward. All right, last topic, and then we will be done with our notes for this. So total change. Now, we have to remember that every time we did net change, we took into account when we moved backwards. Total change we're going to talk about is similar to an odometer. Okay, whereas if you're in a car, whether you drive forward or backwards, it's always going to be added on to that odometer. So the integral from a to b, we're going to just put in an absolute value sign here because that's going to take all of our negative area and it's going to automatically make it positive. So this is going to tell us the total change in position or in amount or whatever our first function is, our original function. It does not tell us the net change, okay? We've talked a lot about the difference between those two. We got to make sure that we're using those key vocabulary words the right way. So it's going to tell us the total amount that we've moved from the start, including the times where we moved backwards. So we're going to do a couple examples and then be done. So we know, let's just sketch out this function. I know that 2t minus 3 is going to start down here at -3, and it's going up. So I know that I have area below and I have area above for this function. So let's evaluate this completely using the calculator, okay? To get the absolute value sign, you're going to press math. You're going to go math. You're going to go over to num. And then you're going to pick the ABS button, okay? So when I do it 0 to 5 of that, and then I do 2x minus 3 dx, oops. I'm going to get, the integral from 0 to 5 of the absolute value of v of t dt. So the total distance that it's moved from 0 to 5 is going to be 14.49999. So I'm going to guess sometimes the calculator does weird things and tries to be super accurate. We're going to say this is about 14.5. Okay. So the total distance traveled from 0 to 5 seconds is 14.5 feet. So make sure if we're talking about total distance that our units align with that. The units should still be feet there. Okay, let's see, we got 3 more examples and then we're done. So we're given a velocity function here, and we want to find the total distance traveled. So we're going to do the integral from 0 to 2 of v of t dt, but total distance, we got to throw that absolute value sign in. So from 0 to 2, we're going to throw in that absolute value sign, put in my function, x sine of x squared dx, and that is going to give me 0.06978. So I'm going to round that to 0.070 to 3 decimal places. They're not giving us units, so that is going to be the total distance traveled from 0 to 2. Okay, total distance, absolute value signs, always. All right, last 2. Using correct units, explain the meaning of the definite integral from 0 to 40 of the absolute value of v of t dt in the context of the problem, and then we want to estimate it. So I'm going to explain this first. We know this is going to be total distance. So total distance traveled. Now we have to make sure in context means you have to have units. The total distance traveled in meters. Remember, distance is meters, not meters per minute. From 0 to 40 minutes. Okay, so we checked off the first part. Now they're asking us to approximate the value using a right-Riemann sum. So this is where we got to be careful, because we know that absolute value means everything has to be positive. So the integral from 0 to 40, the absolute value of v of t dt is going to be approximately, so a right-Riemann sum, I got to go to the right. So these are going to be my values, okay? So base of 12, height of 200, plus base of 8, height of 240, plus base of 4, now height of negative 220, but remember, all of these are going to have to be absolute values anyways, so we're going to treat it like a positive in the end. Plus, and then 24 to 40 is going to be 16 times 150. Okay, now APFRQ, leave everything exactly as it is, and you are done. You are totally fine. You are good to go, okay? If we have to evaluate it, I'm going to put it in the calculator really fast. You should come out with 7,600. And remember, it's the amount, so we're going to say just meters. Okay. All right, last one. We want total distance traveled. We've already dealt with this example a few times, but we have the velocity here, and I want the total distance traveled. So total distance traveled is going to be the integral from 0 to 6 of v of t dt. Oops, it's total, so I have to put in my absolute value sign. And for right now, we are going to our calculator for everything. Everything calculator. We are going to learn later on how to do some of these in by hand, but for right now, everything is calculator. So we come out with 6.486. And again, they don't give us units, so we're going to leave it just as it is. Okay, so conclusion. We should now know how to find net change. Remember, net change is just going to be the integral from a to b of v of t dt. We should be able to find position which is going to be f of a plus the integral from a to b of v of t dt. We know how to find average value, which is going to be 1 over b minus a, the integral from a to b of whatever function they put in there. And then now we know how to find total change, which is going to be the integral from a to b, the absolute value of v of t dt. Okay, so summary, the 4 things you guys can now do with integrals.